a fixed point. The equal distance is the radius. The fixed point is the center. But to manipulate the circle, we'll have to come up with more than a verbal or visual definition. So let's take the circle, drop it onto the Cartesian plane, and derive a general equation for it. Here is a point Pxy. It forms a right triangle with sides x, y, and the radius r. We also know that the center of the circle is the point 0, 0. The Pythagorean theorem provides a straightforward method of calculating the distance between 2 points. Here are 2 points, A and B. D is the distance between them. D is found by taking the difference in the x-coordinates of the 2 points and squaring it. Then take the difference in the y-coordinates and square it. Add them together and take the square root of the sum. Applying this method to the circle, the radius r equals the square root of x minus 0 squared plus y minus 0 squared. To rid ourselves of the square root sign, we'll square both sides of the equation. R squared equals x squared plus y squared. And since all points on the circle are the same distance, r, from the origin, this is the equation of a circle centered at the origin. But what if a circle doesn't happen to land smack on the origin? Let's say the center is at the point 2, 3. To find the distance between the center and Pxy, use the Pythagorean theorem again. The radius equals the square root of x minus 2 squared plus y minus 3 squared. And again, we'll square both sides. Notice how the equation displays the original given information, with 2 and 3 being the coordinates of the center. So, the general equation for a circle of radius r and center at point AB is r squared equals x minus a squared plus y minus b squared.
Charlie, it's gonna be a while before the ship's ready.
Don't worry, Ed. We've got all the time in the world.
Another way of examining circles not centered at the origin is in terms of transformations. Transformations can be applied to any of the conic sections. In a simple translation, each point on the original figure moves the same distance and direction to form an exact replica. Here's a circle centered at the origin. If the radius of this circle is 5 units, then the equation is x squared plus y squared equals 5 squared, and we can write it either way. Now we'll apply a translation to the circle, moving it to a new position on the Cartesian plane. The center of the circle is now at point 10, 7. Let's determine the translation that moves or maps the original circle onto the image circle. The center of the image circle is, as we said, 10, 7. So the x value of the center and all points on the circle have been increased by 10. And the y values have been increased by 7. In transformation notation, the translation named t maps the points of the original circle, xy, onto the points of the image circle. X plus 10, y plus 7. That's the transformation. To find the equation of the image circle, we'll temporarily introduce a new set of axes, u and v. This makes life a bit easier, since the image circle is now centered at the origin, even if it's the UV origin. The radius is still 5 units. So, in terms of u and v, the equation must be u squared plus v squared equals 25. Now all we have to do is convert this equation into terms of x and y. Let's look at one representative point on the image circle. Point 50. In the original xy terms, this point is actually 15,7. That is, the u coordinate equals the x coordinate minus 10. And the v coordinate equals the y coordinate minus 7. We can confirm these relationships for any point on the circle. Substituting into the UV equation gives us the equation of the image circle in xy terms. X minus 10 squared plus y minus 7 squared equals 25. So there it is, the equation of the image circle in terms of x and y. But be careful, even though the equation has minus signs, the transformation has plus signs.
You know, Charlie, the temple has been really helpful.
Well, Ed, we've seen the circle, but it's those other shapes I really don't know much about.